Everyone, welcome to the Multimodal Weekly webinar series hosted by 12 Apps. To some of you who are new, we have been meeting every week, every Friday actually, over the past 7-8 months or so. Here's some of the topics that we tend to cover on a weekly basis. News research in multimodal AI and foundation models, innovative application of multimodal in different verticals. Since we focus a bit more on video, sometimes when community members talk about their video and multimodal projects that they like to share. And oftentimes we have internal team members share tutorials and guides on using technology, including platforms and API. Some of the recent sessions were arranging a speaker persona from researchers working in video engineering and fundamental of modeling architecture to startup founder working in open source and infrastructure for Gen AI to developers who are building the newest coolest tutorials and use cases leveraging multimodal AI. So for today's session, I would like to welcome Hila Chefer, who is actually a second-time speaker of this series. Last year, we hosted her for a session on her previous paper called Conceptor, if I remember correctly. It was a very awesome talk that looking at the work of diffusion models. And for today, she actually will give a presentation on her latest work called Lumiere, which is a space-time diffusion models for video generation. This is the work done during her internship at Google Tel Aviv, and definitely saw like some blog posts, website, and social media release about Lumiere over the past few weeks. So I'm very super excited to have Hila with us today to give a deeper dive into the motivation overview, technical deep dive, and novel use cases of Lumiere with our community members. Just a quick just note, if you have any question, feel free to send them on the Zoom chat and I can curate them and send them over to Hila to answer those questions as you finish any major part of the presentation. So I know we have a lot to get through to the talk today, so I'll let you start sharing the screen and go ahead with the talk.
Okay, thank you so much for that awesome introduction, James. Can you see my screen?
Mm-hmm.
Okay. So as James said, my name is Hila, and I'll be presenting our latest work called Lumiere. Lumiere is a space-time diffusion model for video generation. And then before, oops, the presentation kind of jumped there. Before we dive into the actual content of this talk, this paper is a joint work of many very talented people. So I just wanted to take a moment to kind of acknowledge that this work was done jointly with Google Research in Tel Aviv and in Cambridge. So many great people have worked on this, kind of wanted to give them their moment. It was really tedious work for a few months for a lot of us. So just wanted to give some recognition to the other co-authors of this amazing paper. And I'll skip the introduction about me because James did it so wonderfully. So let's take a look at some of the topics that we're going to go through during this talk. So first and foremost, Lumiere is an inflated text-to-image model. So we'll go over what it means to basically inflate a text-to-image model into a text-to-video model. Then we're going to deep dive into Lumiere's architecture, basically how we did the inflation and what's so special about Lumiere versus the alternatives. We're going to touch on the initialization of the model because we did see that the initialization is something that really helped the model converge and what was very significant in the results that we got from Lumiere. We're going to talk about the spatial super resolution that we're applying, and then we'll wrap it up with results and applications, which I'm sure is the most exciting part for all of us. So as I said, we'll get started on text to video through text to image inflation. So the basic intuition is this. We do know that we have these amazing text-to-image models that are able to generate diverse images based on a text prompt and a pure random noise. But then the issue or the gap between image generation and video generation is that for different random noises, we're getting different images that are kind of uncorrelated with each other. So both spatially and temporally, these images are not constituting an actual video. And then the idea behind inflation is going to be very simple. Let's take this model that knows how to generate distant or distinct keyframes and add temporal layers such that these temporal layers will add connections between each one of these unrelated frames. So basically, we leverage the information or the prior learned from the text-to-image model and kind of distill that into video generation with those temporal layers. So those temporal layers will actually turn this inconsistent information into information that is consistent both temporally and spatially. But then the biggest issue or the biggest roadblock towards achieving a good video generation is that video generation is very expensive. So if we go back to this scheme, we do know that those blue layers are already pretty heavy, right? They have a lot of parameters. And then we also added those orange inflated temporal layers. And also if we want to kind of generate the entire, whoops. If we want to generate the entire temporal duration of the video, we would have to generate something like 80 frames, which is what we generated for Lumiere, okay? So it's going to be very expensive in terms of memory. Just think about how many images you can fit in your GPU, in your A100. It's not a lot. I mean, it's definitely not 80 images. So there's going to be a technical difficulty in actually getting the model to generate all the frames at once. So the common approach that people came up with prior to Lumiere was this. First, we generate distant keyframes. You can think of those distant keyframes as key points throughout the video. So we'll generate the entire story, and we'll just generate kind of landmarks throughout the story. And then what we're going to do is we're going to take those landmarks and fill in the missing information in each one of those windows. So let's take a look at how this process is done. So what we're seeing here is basically what we call the base model, the model that generates the distant keyframes. So say I want to generate this video of a teddy bear surfing. What I'm going to do is I'm going to first generate those distant keyframes. And then after I generate those distant keyframes, I'm going to take each one of those windows where I'm missing the frames and kind of do what we call frame interpolation. So we're going to fill in the missing parts from those keyframes that we currently have. And then basically arrive at our final video, which is interpolated between each one of those windows. So these windows are typically not going to have an overlap between them, which is going to be problematic for us. So let's take a look at some of the problems with the approach that I just described of generating distant keyframes and then interpolating in each one of those windows. The first issue is a rather technical issue. Say we want to generate, again, 80 frames. And say our memory constraints only allow us to generate 20 frames at once, right? This is just the physical limitation of the hardware that we're using. So if we want 80 frames, we would need to generate first 20 distant keyframes, and then temporally interpolate them into 40 keyframes, and then again interpolate them into 80 keyframes, which means that we're kind of using a convoluted system of several temporal super-resolution models. So each inference is going to be actually constructed of a few temporal super-resolution models. So this is just a technical limitation of, instead of just doing inference once, we're going to need to do inference 3 times. One time with the base model to generate distant keyframes, and then 2 temporal super-resolution. If I'm not mistaken, Imagine Video did 3 temporal super-resolutions. So this is kind of a convoluted system. But then there's another issue that I think is more nuanced and more noteworthy, because if we take the previous slide, we can kind of speed up the inference of diffusion models to kind of overcome this limitation. But the limitation that I'm going to show you now is more profound and cannot be kind of overcome by just using better hardware or faster hardware. So let's take a look again at Imagine Video, again, a cascaded model that uses temporal super-resolutions. This is a video actually from the website of Imagine Video of a wooden figurine walking on a treadmill. And if you take a look at these frames kind of carefully, you can see that the leg is jumping, it's cutting off, it's jittery. So we're seeing inconsistencies in the motion. And then the analysis that we did in the paper is called XT slice analysis. So basically what XT slice analysis means is that we're going to take this spatial part of the video that shows the legs of the figurine, and we're going to show the legs throughout the video. What you would expect is that since this is repetitive motion, you would expect kind of wave shapes of the legs walking one in front of the other. But basically what you can see with the temporal inconsistencies, you'll see the jittering and the cutting off effect over here. You can see that the leg kind of disappears in some of the frames, as you can see here, or the leg jumps in some of the frames. So now we're kind of asking ourselves, why does this happen? Or what is the cause for this issue that we're experiencing? So we had 2 hypotheses that I'll share with you. The first one is, if you recall, the base model had to generate distant keyframes. So say we wanted to generate a video at 16 FPS, right? The base model would generate something at 4 times less the FPS, right? The frames per second rate. So it would generate something at 4 FPS. And then the keyframes are going to be very distant from each other. And if you think about it, the task of generating distant keyframes that can be later interpolated into actual motion or actual leg motion is much harder than just generating consecutive keyframes or consecutive frames in a video, right? Because consecutive frames will be very similar to each other. The leg will maybe move a bit. But the task of the base model is much harder than that. It needs to generate distant keyframes at a very low FPS, such that later the temporal super resolution model can interpolate them into something that makes actual sense in terms of walking. So this task is much harder than just generating all the frames one after another. And then another issue is that, as we saw in, if Zoom will allow me to kind of go backwards, we generated all the missing frames in non-overlapping windows. So there's no global consistency or no global information about the motion between each one of those windows. So this window is not aware of what the other windows have done. It's only aware of the keyframes that it got to interpolate, and it's kind of guessing what happened in the middle. So this is called temporal aliasing. And you can think about the classic example of a fan, and you can see the fan, a few frames of the fan, of kind of, the big sticks inside the fan. And just by seeing those distant keyframes, do you know which direction the fan is actually turning? Not really. Or you can think about a person doing jumping jacks and then returning his legs to the middle. When you see a frame with the legs in the middle, do you know if the person jumped outside before or did it just start jumping? So temporal aliasing just means that you lose a lot of information by just seeing those distant keyframes and not having global context. So we hypothesize that the reason for the jittering that we see here is that A, it's very hard to generate distant keyframes, right? It's a much harder task. And 2, because of the temporal aliasing in each one of those windows that we need to interpolate. So there's no global context or global coherency to the motion. So this is mainly the issue that we try to tackle with Lumiere. And then Lumiere's approach is going to be very simple to tackle all this. We're going to generate all the frames at once instead of generating distant keyframes and then doing temporal interpolation, which allows us to learn globally coherent motion. As I said, fix the problem that we saw in the previous slide. And it's also going to solve that convoluted system of many temporal upsampling models. So it's going to be a simple framework, just a single model generating the entire temporal duration of the video. So just to give us some motivation as to what this does in terms of the wooden figurine, what we did here, we took the first frame from this video with Imagine Video, and we used Lumiere with image to video in order to generate a video that kind of corresponds to the original video in terms of the content. And as you can see here, the motion is much more globally coherent. So you can see the legs are actually moving as they should, right? We're kind of getting rid of some of the effect that we saw of the jittering and jumping before, thanks to the fact that we're generating all the frames at once. Okay, so then the main question becomes, how do we do that? Because as I said, whoops, again, PowerPoint is not my friend today. As I said in the beginning, this is a computationally challenging task, right? The reason that we had to generate those distant keyframes and then do temporal super resolution was because we didn't have enough computation to kind of generate all the temporal duration of the video at once. So we're going to have to do something to the architecture to mitigate that computational complexity, to kind of make it easier to generate all the frames at once. And that's going to be the base of Lumiere and what I'm going to talk about. So before we dive into Lumiere's architecture and how we actually made it possible, do we have any questions, James, up until now?
No, I don't see any question in the chat at this point.
Oh, okay. Really? Oh, wow. Okay. I guess I'm either doing a great job or you're all kind of sleepy. If you have questions, please feel free to kind of flood the chat with the questions. I'd be happy to answer them. Okay, so as I said, what I need to explain to you right now and convince you in right now is how we actually overcome that technical limitation of not being able to generate a lot of frames at once. So this is where our architecture comes into play. So as before, we start with the naive inflation architecture. So what we're seeing here is just basically the Unet, the text-to-image Unet, and the blocks here, the blue blocks here, are inflated with temporal layers, as I said in the beginning. And in a Unet, we do spatial subsampling, which means that if we're getting this noisy video as input, right, these 80 frames as we want it to kind of generate 80 frames, we're doing spatial subsampling in each one of the layers or the levels of the Unet. So you can see that here, the spatial resolution is, say, 128 by 128, which is the resolution for Lumiere. Here, the resolution is going to be slightly smaller, say by a factor of 2. And in the bottleneck, the spatial super resolution is going to be the smallest. And then we have the upsampling, which will upsample the spatial super resolution back. But then one of the issues that we kind of targeted here is that there is no temporal subsampling. So the reason why this is so computationally expensive is because all these layers here, all these inflated blocks and original text-to-image blocks need to operate over the entire temporal duration of the video. So if we have 80 frames here, it's going to be 80 frames here and on these lower resolutions as well. So the temporal dimension, unlike the spatial dimension, is not undergoing subsampling, which makes it very expensive to process the information, even here in the bottleneck, where it should be kind of easy to shove a lot of parameters because the information is kind of condensed, okay? So this is what we're going to target in Lumiere. So basically, instead of just doing spatial downsampling and upsampling, we're going to add temporal downsampling and upsampling. So every time we do spatial subsampling or downsampling, we're going to do temporal downsampling as well, such that here in the bottleneck, we'll have kind of a very condensed representation of the video, both in space and in time. So here we're only going to have to deal with 1/4 of the frames that we had to deal with here in the beginning. And then if we shove a lot of parameters here in the bottleneck, it's going to allow us to kind of put a lot of computation here where it's less expensive, and then do the heavy lifting here in the condensed representation, which is kind of similar to the intuition of latent diffusion models, maybe, if you will. So this condensed representation of units was done before. The first time that we saw it was in the context of medical processing in the paper that we're seeing here. And here we're leveraging this idea or this concept for video generation. So basically, as I said, what we're seeing here are the different blocks of the Unet for Lumiere. So the blue blocks that you're seeing here are inflated blocks based on only convolutions, and all the attention operations by Lumiere are going to be condensed here in the bottleneck. Why? Because attention is a computation that is expensive in terms of space, right? We know that it's quadratic in the dimension of our input. So basically, we're going to shove most of our parameters and most of our compute here, as I said, in the bottleneck, in order to kind of do the heavy lifting on a very condensed representation. So the layers of the model are constructed as follows. You see the pre-trained text-to-image layers, right? As we said, we have an inflated model. So we have our original text-to-image layers. And on top of that, we add the convolutional layers or the attention layers in the inflated blocks. And as you can see here, we have this skip connection construction where the information from the pre-trained text-to-image layer is added to the information that is outputted from the temporal inflated layers, okay? So one more thing I need to tell you is how we do the temporal down and up sampling, right? Because that's the entire idea of Lumiere, as I said in the beginning. So the way that we do that is very simple and intuitive. So the temporal downsampling is done by a 1D convolution, and the 1D convolution is on the temporal dimension. So basically, this 1D convolution is going to pass information between these frames. So the first frame is going to get context from its neighboring frames, its close neighboring frames. The kernel size is like 3. So what we're going to do here is we're going to create a contextualized representation for each one of the frames, such that the frame kind of knows its neighboring frames. And then we're going to do striding. So striding is something very simple. We're going to subsample each second frame, okay? So the 1D convolution is kind of passing information between frames and the neighboring frames. And then we're going to do the striding and take each second frame. So what we're seeing here in the lower resolution is information that is subsampled both spatially and temporally, such that we subsampled each second frame, okay? And here in the bottleneck, we subsample each fourth frame in relation to the original information. So if we have here 80 frames, in the bottleneck, we'll only have 20 frames to process, which, as I said in the beginning, is something that is computationally feasible for our model. And then the temporal upsampling is going to be just the mirror of the temporal downsampling, obviously, So we're going to do first frame duplication, meaning frame 1, 1, 2, 2, 3, 3, and so on and so forth. And then we're going to do the same 1D convolution to kind of pass information and make the distinction between the frames. Okay? So this is the entire scheme of the temporal down and up sampling. Okay, so before we move on to the next part, this basically allows us, by putting most of the parameters here in the bottleneck, most of our computation is done on this condensed representation that is feasible to kind of compute. So that's the basic idea behind Lumiere. Generate all the frames at once to avoid the aliasing issue that we saw in the beginning, while also kind of keeping it computationally feasible. So if you have any questions, do we have any questions, James? At this point?
I don't see anything on the chart for now. But
does anyone want to kind of jump in and ask something? I mean, does anyone have a question?
Yeah, let's wait for maybe 1 or 2 minutes for folks to, anyone want to ask a question.
Okay.
I can ask something, just
sure.
maybe curious. I think there was a slide right before this where you mentioned like a specific part of the architecture that requires more compute. Yeah. Attention inflation block versus convolutional inversion block. Can you extrapolate on this point? What is the attention one requires more compute?
Yeah, okay, so basically in the model that we're using, the text-to-image model, and also in Stable Diffusion Extra Large, they put the attention calculation in the bottleneck as well. So this is kind of a famous trick because attention maps are heavy in terms of memory. So if we have kind of a sequence of size L, so the attention map is going to be size L squared. So the longer the sequence is that we're processing, the more kind of memory that we're going to have to store in the attention mechanism. And then a famous trick to kind of overcome it and have the attention operate on a lower dimension is to just shove it in the Unet bottleneck, because the Unet bottleneck is also always where the information is most subsampled. And then both the spatial and temporal attention is going to be concentrated on this bottleneck. And then the spatial attention is just the regular attention that we know and love from Stable Diffusion, where each one of those frames is kind of processed independently. And the temporal attention is an attention mechanism that is kind of a needle. So you take each one of the patches, and then you kind of do attention for the patch with its corresponding patches across the time dimension. So you'll have this first patch here, and this first patch here is going to do attention with the first patch in the second frame and the first patch in the third frame, and so on and so forth. So it's called needle because it's kind of like sticking a needle inside the patch across the time dimension. And then if we had a lot of frames, say 80 frames, then this would be kind of more computationally expensive than if we have 20 frames, because that needle attention is kind of dependent on how many frames you process at once.
Perfect.
So
thanks for highlighting that. And maybe you also shared that in the previous slide, but can you specify where in the Lumiere architecture that it performs spatial and, oh, here we go. So the red one is spatial, up and down sampling. The green one is temporal, up and down sampling. So basically you are performing both spatial and temporal processing concurrently, right?
Yeah, so the idea is that the original Unet, the inflated Unet that we're using, so basically the text-to-image model already does the spatial subsampling. It's part of the network. It uses kind of convolutions to subsample the input that we're having. And then each time that the Unet, the original text-to-image Unet, does spatial subsampling, we'll also do temporal subsampling with our additional layers. So just as we inflated the other layers, right, that we're seeing here, so just as we inflated the convolutional blocks and the attention blocks of the original model, we'll also inflate the spatial subsampling blocks. And the kind of parallel to a spatial subsampling inflation is temporal subsampling or upsampling, right? So each time that the original text-to-image model does spatial subsampling, we'll do temporal subsampling. And by the way, this trick of kind of using information from a text-to-image model is a very useful one, because we do know that image generation and video generation are kind of closely related, other than that inconsistency issue between the frames. So when we actually inflate an original text-to-image model, we can kind of make our model converge much faster. And also, we do know that we do not have a lot of video data. So given that you're kind of using an original text-to-image model and inflate it with additional temporal layers, you can make the model converge much faster thanks to that strong prior that you have from your text-to-image model.
Perfect.
So does anyone else have any questions about that? Anyone? Okay.
Yeah, I think we moved to the next part.
Yeah, I guess that. I'm either doing a really good job or a really bad job. Okay.
People are just trying to grasp the complexity of your presentation.
It's okay, by the way, if you have simple questions. I'd be happy to kind of go over again any part that you think is unclear. So anything you want to ask, just feel free to jump ahead. It took us some time, a few months to kind of get everything here right as well. So I do get that this is a bit complex for a 1-hour talk. Okay, so assuming we do not have any other questions, let's move on to the other topic that I wanted to talk about, the initialization. So as I said right now, in response to James' questions, one of the things that we would want to do most is kind of preserve the information as much as we can from the text-to-image model, right? So we would want to kind of initialize the model to mimic the text-to-image model as much as we can, because we would want the starting point of our inflation model to be just the text-to-image model in order to kind of extract as much information from the prior from the text-to-image model. So again, our intuition, at initialization, stay as close as we can to the text-to-image model because that's a pretty good starting point. And then have the temporal layers kind of enforce the consistency across frames from that point. Okay, so if we take a look at the original inflation scheme that we saw in the beginning, right, we do not have temporal downsampling. Then thanks to these skip connections, what we can do is just zero initialize the linear projections before the skip connection. So when we zero initialize those layers, basically what this block is going to do is just pass the information from the text to image layer, right? So just basically at initialization, what this does is basically nothing, right? The inflated layers are finally linear projected with zeros. And then the output is going to be just equivalent exactly to the output by the text to image model. And then again, if we take a look at the frames at initialization, if we start from just different random noises, we'll get distant frames, right, that are unrelated to each other temporally, but they are meaningful. They correspond to our text prompt because we initialized our model such that it started from the original text-to-image model, right? So that's basically the intuition of the initialization. But now we also added those temporal down and upsampling layers, right? So let's take a look at what happens if we randomly initialize the 1D convolutions here and here. So if we randomly initialize those 1D convolutions, all the information here is going to be basically out of distribution, right? Because we passed a random kernel through all those frames. So this is going to be out of distribution. This is going to be out of distribution. Everything here is basically going to be out of distribution for the model. And then we're kind of going to get those random frames given random noises, and then lose all the prior from the text-to-image model that we had, that we wanted to kind of preserve to get our model to start from a nice starting point that is similar to the video generation. So we need to come up with another way to initialize those convolutions because we now do not have that skip connection that we can just zero initialize, right? If we zero initialize those convolutions, then the information here is just going to be basically zero, right? So zero initialization is not good. But the alternative we came up with is just identity initialization for this information. So let's see what happens when we do identity initialization. So basically, we started with our 80 frames, right? As I said in the beginning, our motivation is to generate 80 frame videos. And now the temporal downsampling is just going to do the convolution is just going to be identity, right? So it's not going to do anything to the input. And then the strat is just going to subsample each second frame. So in the level here, in the second level of the unit, we're going to have frames 1, 3 through 77 and 79. And again, the temporal downsampling is going to take out each second frame, right? Because our 1D convolution is just initialized to identity. And then in the upsampling, we're going to do frame duplication and then nothing. So basically, this is going to be 1, 1 through 77, 77. And now notice this point, because this is the critical point. You're kind of doing a skip connection here between the identical resolutions of the Unet. And here you're going to connect frame 1 with frame 1, which is okay. But then frame 3 is going to be also connected or added to frame 1. So you're kind of adding here information that is unrelated, right? Frame 1 to frame 1, but frame 3 to frame 1 is going to be a bit out of distribution. This issue gets worse when you come up to the finest level of the Unet, where you have frame 1 duplicated 4 times through frame 77 duplicated 4 times. And the skip connection here is basically going to leave you with just frame 1 that is valid, and then 2, 3, and 4 are going to be invalid. Now, this is one of the prices that we need to pay for temporal downsampling. I mean, at least for Lumiere, we couldn't think of another way to initialize the model that keeps it closer to the text-to-image model. So this is the closest way we could come up with. And the way that this looks at initialization is that you'll see that each fourth frame looks valid, right? It looks like a good frame because you kind of added it in the skip connection to the right counterpart in the downstack. But then the frames in the middle are going to be just a bit out of distribution. So you can see that some information here actually makes sense. You can see the interpolation between the unrelated frames and the related frames. So each fourth frame is going to be okay and valid, but then the frames in the middle are going to be a little less valid. So you lose some of the prior that you had from the text-to-image model. But I do want to convince you that this identity initialization gives us something, meaning that we didn't just initialize the model with those downsampling blocks with identity just for nothing. So what you're seeing here is a small experiment that we did with identity initialization for the temporal downsampling and upsampling versus the standard initialization, where we just initialize them to just random things. So you can see here the orange line for the standard initialization and the blue line for the identity initialization. And you can see that even though the entire video is not kind of sticking to the text-to-image prior as we would have wanted it to, the fourth frames that make sense and the frames in the middle that kind of make a little sense and are kind of slightly out of distribution are actually very helpful for the model. So you can see that both the starting point is much better, which is kind of understandable, but then also when we train the model, the convergence of the identity initialization is better consistently across epochs than the standard initialization, which kind of gives us an idea of how much the initialization in this case can be very helpful to your convergence of the model, because the text-to-image model that you started with kind of has a lot of useful information that you don't want to lose and you want to leverage when you kind of train your temporal layers. So this is on initialization. And James, do you have any questions or no again?
Yeah, I think this one is, nothing so far. I think this topic is also even more technical than the previous one. So I felt like people don't have much like idea.
Okay, does anyone have any questions on this or anything you want to discuss or go over again? Okay, did someone say anything or was it just my imagination?
No. Yeah, just me. But yeah, I think the main point you want to emphasize here is just the choice of identity initialization, right? And how that like is a better option than standardized when you're in training.
Yeah, that's the point. And actually the point is, if you're training a video model with low resources, which is basically, I think, most of us, right, who don't work at huge companies, it is better to kind of select your initialization point from something that actually makes sense, because it will help your model converge much better. Other than the fact that when you do the temporal downsampling, you can actually generate a lot of frames together and then avoid the aliasing issues. Okay, so let's sum up the key insights that we had when we constructed our space-time unit. The first one was compress both space and time and do most of your computation on the compressed representation, which is something that is similar to the intuition behind latent diffusion models, for example. We kind of generate this latent that has kind of condensed information on our input, and then we do the heavy lifting there, and then we can basically process the information much more effectively. And then the second thing that we just showed was that initialization actually really matters. So if you initialize your model wisely, it can converge better. Okay, so let's touch a bit on spatial super resolution. The idea behind spatial super resolution is this. So basically, our original model is based on Imagine inflation, and Imagine generates videos at resolution of 128 by 128, which is not a lot. So we would want to have kind of an additional model that takes our low-res information and upsamples it into a higher resolution because we want to kind of generate high-quality videos. But then the issue is that now the model works on a much higher resolution input, right? It works on 124 by 124 resolution. So even with the trick of the 3D unit that we did before with the temporal downsampling, this is not enough. Like the additional overhead from the much larger spatial resolution will make it computationally, again, infeasible for you to process the entire temporal duration of the video at once. And this is just a given, something that we have to deal with. So what this causes is, initially what we did was we generated or did the SSR in distant windows like here, which is similar to the temporal upsampling that we saw in the beginning, right? So we take each one of those windows, we process 10 frames at once only, and we do the SSR for those 10 frames. And then we move on to the next window of 10 frames and so on and so forth, and then we've upsampled the entire video. And then what we notice, I hope you can see it here in the video on the left, but if not, you have the XT slices here again. You have those boundary artifacts. So between each set of 10 frames that we saw in the previous slide, you can see a small jump spatially. So you can see it here and here and here. And the reason is, again, we do not have global context. And when you do not have global context, whether it is temporally or spatially, things go wrong, right? We saw that in the temporal dimension, it only makes sense that it will also happen in the spatial dimension. And here, as I said in the beginning, you cannot just use the 3D unit trick because your input information is that much bigger. It's 1024 by 1024. So it won't help you process the entire 80 frames at once. So what we did is we used a technique called multi-diffusion. And then this talk is not really about multi-diffusion, so I won't get into details a lot. But then the intuition behind it is very, very simple. Instead of just doing the SSR in unrelated windows, we're going to have a sliding window, right? Similar to a convolutional kernel. And then we're going to average the prediction across the predictions of the overlapping windows. So basically, this frame here is going to be joined for this window and this blue window here. And then the prediction for this frame here is going to be averaged across the prediction by this window and the prediction by this window. And then the averaging effect kind of mitigates over the boundary effects that we saw in the previous slide. So here you can see on the left, the window approach. And then on the right, Lumiere's approach with multi-diffusion for the SSR. And you can see that those boundary artifacts that we have between each one of those windows are kind of mitigated by the averaging, which makes a lot of sense. Okay, so I guess I won't ask if we have any questions anymore, and just James jump in if we have any questions.
Yeah, of course.
Okay, so I hope it's all clear. So we had kind of the key design choices for the model, which was the temporal downsampling and the initialization. And then we also had a similar intuition for the spatial super resolution, which kind of ties together with our intuition for the temporal super resolution, which was that generating things in distant windows does not work well. So you kind of have to find a way to integrate information across those windows that you're processing. Okay, I will say that getting rid of the SSR is something that is kind of encouraged and helpful because you kind of don't want to deal with another model that you need to train. So basically what I think would be best is just to operate on a latent diffusion model, which is similar to stable diffusion. Take your original input that is 124 by 124, train an autoencoder just to do the super resolution part, and then do the entire diffusion process on the latent representation, which can be 128 by 128. Because that window approach for SSR is pretty expensive in terms of time. You have to now perform SSR in sliding windows. So you have to kind of operate a lot of times with the SSR to get those averages correctly if you want to avoid the boundary artifact. So I do think that getting rid of the SSR with the latent diffusion model is something that is pretty simple to do and would work quite nicely. Okay, so let's go over to the results and applications. So the first result that I kind of have to show you is text-to-video generation, right? Because that's kind of the reason why we train the model. So as you can see here, the results are kind of temporally consistent, which I really love. I kind of saw those results and compared them against our baselines, and I was really impressed by the fact that when you generate the entire temporal duration of the video at once, you get rid of a lot of the temporal artifacts that we saw originally in some of the models, such as Imagine Video, even though we didn't train on a whole lot of data that is kind of prominent in our work. So one of the key things about Lumiere that I like is that it is an inflated model, and it is based on text-to-image. So basically, almost all the things that we did for text-to-image models, we can kind of migrate to text-to-video pretty easily because basically the architecture is almost the same, give or take the temporal downsamplings and the additional temporal layers that we have. So the first thing that we did was image-to-video generation. So if you want to condition your generation on an image, you can just fine-tune the model. And then during fine-tuning, you concatenate the image to your noisy latent that you're getting, and you're training the model to reconstruct the video. So basically what we did during training, we took a video, we took the first frame of the video, we conditioned the model or added to the model that information of the extra frame, and the model is going to learn to use it very quickly because this information is very useful. If you think about it, just by duplicating the first frame, the model can already achieve a pretty low loss, right? So the first frame contains a lot of useful information for the model to denoise the video. So it learns to kind of rely on the first frame in order to generate the next frames. So basically, this is just fine-tuning of the model with the same data. So you don't need an extra data set. And then during inference, you can take any image that you want and then generate a video based on that image once you condition on it. So this is a really famous painting, and we made the girl wink and smile, which is one of my probably favorite results in the paper. So just to show you some results, text-to-image and text-to-video and image-to-video generation. One of the things that I really like to point out about this slide is both the temporal consistency and also the high quality of the videos that we're getting, which is partly because we use the very powerful text-to-image engine as our base model. So the video model already knows to generate really high quality stuff just by taking a lot of information from the text-to-image model. So the next thing we wanted to do is kind of similar to things that you have seen probably in papers or in models like AnimateDiff. So the intuition was this. Say I want to generate a video based on a reference style. For example, here, the sticker style of this pine tree. Then I can fine-tune the text-to-image model, so the text-to-image weights, right? And then I get these amazing results that resemble my style. And then I would just want to plug and play the fine-tuned text-to-image weights into the video model, because the video model was basically just an inflation or an extraction or an extension of the original text-to-image model. So basically, with Lumiere, we froze the text-to-image layers, and we only trained the temporal layers. So it should technically work. But then when we did this plug-and-play approach, we saw those very, very unpleasing visual artifacts that you're seeing here. So basically, I didn't get what I wanted, which was these results, these nice results animated. I got kind of grid artifacts and something that was very weird. So the motivation or the intuition behind this is Lumiere is generating the entire temporal duration of the video at once, right? So these temporal layers are actually doing a lot of work in making the videos consistent. And there's a lot of motion also in Lumiere and what we're generating. So it makes sense that when we shift the distribution of the blue layers, the orange layers now do not know how to interact with the information from the blue layers. Because basically, we kind of traveled away from the distribution that those orange layers know. So the orange layers cannot be expected to kind of interact with the blue layers once we have shifted them from the distribution, right? So just a basic intuition. And then what we kind of thought about on how to solve this, the idea came from GANs. So in GANs, what we saw was that we can take the original GAN weights and the fine-tuned GAN weights and interpolate between the original and fine-tuned GAN weights to kind of control how much of the style we want to take. So we thought about doing the same, interpolating the text-to-image weights between the original text-to-image weights and the fine-tuned text-to-image weights. So basically here, we're only touching the text-to-image layers. We're not touching the temporal layers. And the goal is just to take the weights that kind of diverge from the distribution and bring them back to a point that is closer to the distribution that the temporal layers know. So we kind of grid search this hyperparameter alpha, where alpha is going to weight how much information we're going to take from the fine-tuned text-to-image model and how much information we're going to preserve from the original text-to-image model. And what we saw by doing this, just that, is that we were able to kind of bring those layers closer to the distribution that the orange layers know. But here's the thing that I like most about this feature. And this is a feature that I worked on for quite a lot of time, so I had a lot of time to kind of connect with it emotionally. The feature that I liked most is that you can see that the motion is actually stylized. So it's not just that the style of the videos changes by the reference image. The style of the motion kind of incorporates or adapts itself to the spatial style. And the hypothesis is that during the training, the temporal layers did train on motion like this. So this coloring motion or popping out motion, it did see these videos that are similar to that motion. And then when we did the interpolation, we kind of brought the weights to a distribution of weights that fits those videos that the model saw during training. So basically, by doing the interpolation, we brought the weights closer to the distribution of the temporal layers, and also brought them to a point where the temporal layers know how to kind of relate that special motion to that spatial style. So I kind of want to show you an example that we curated of several styles. And then you can see that this is a more realistic style. So the videos here are going to show more realistic motion. So the bear is actually dancing. We do have some information popping out or glowing, but and then this style reference gives us more of a 3D motion, especially with the lion. You can see it kind of moving around like a 3D object. Here you have some illustrated art where the art is kind of popping out of the image and kind of constructing itself from the image. And again, some more realistic styles. So basically, one of the coolest features was that we were able to connect the spatial style with the corresponding temporal style due to those interpolations that brought us closer to the distribution that the temporal layers know. And this is something cool that I don't think that I've seen before in any of the other work. So I was pretty excited to see those results. Kind of an integration between a spatial prior and a temporal prior. And this was only by manipulating the text-to-image layers. So we didn't touch the temporal layers at all. Okay, so another thing that we can do is cinemagraphs. And then the meaning of cinemagraphs is you're taking an input image and you're, as a user, selecting a region in the image that you wish to animate. And then the model needs to kind of animate only that specific region in the image. So basically, everything else needs to remain still. And as you can see here, only the butterfly is changed, or only the butterfly is animated. So the way that we do that is, again, we fine-tune the model. And the way that we fine-tune the model is that each one of the frames in the noise is going to be conditioned on its corresponding frame. So the first frame is going to be conditioned on the clean signal. And the reason that the first frame is going to be conditioned on the clean signal is that we want to kind of preserve the content that exists in the first frame, right? We want to preserve the butterfly. So basically, we have to condition somewhere in the model on the clean signal. Otherwise, the model will not know to recreate my specific butterfly. So the first frame is conditioned on the clean signal. And then the next frames are going to be conditioned on the signal where we black out the pixels that we want to animate, okay? So during training, what we do, again, we take original video, condition the first frame, the first noisy frame on the first video frame, condition all the other frames on the original frames from the video where you black out the part that you want to kind of animate. And then the model will learn to copy all the information outside the black box and only animate the information inside the black box. Again, deep learning learns how to use shortcuts. So the model knows that it is best to copy all the information that is not blacked out. So that's what the model is going to learn to do. So this is how cinemagraphs are done. I see that we have a question, right, James?
Yeah, we actually had 3 questions.
Oh, wow, yeah, great. Finally. Okay.
Well, I think, I'm just going to ask them right now because maybe some of them. I think there's one question probably refer to the architecture, the stylized generation. He asked, what is, can you go back to that slide, actually, the previous one?
Yeah, the first one.
Yeah, I think around here, he basically asked, what is the temporal layer and spatial layer again? Are they in the Unet architecture for diffusion model?
So the spatial layers are basically the text-to-image layers that we took. So as I said, Lumiere is an inflated model. So we take the text-to-image layers and we add with the skip connections, if you remember, additional temporal layers. So the temporal layers are the only layers that we trained for Lumiere. We do not touch the spatial layers. The spatial layers are locked. And the spatial layers are just the original text-to-image layers. And then the idea behind this is similar to the idea behind animate diff. If we froze the text-to-image layers, maybe we can take fine-tuned text-to-image layers and just inject them into the model. So that's the basic intuition. Is that clear, or is there anything else that we need to explain for this?
Yeah, I think that's clear.
Okay.
And then Magox basically asked, well, she said, great presentation, really impressive results. Would the code and model be publicly available?
It's not up to me. I'm sorry. That's a question that I cannot answer.
Yeah. And then finally, Mindang asked question, what is the longest video the model can generate? How about the inference time for 10-second video?
Yeah, okay, so basically, since we're not doing, so there are ways to do the encoding, because we do need temporal encoding, right? So each frame needs to know its location inside the video, because otherwise the information is going to be just, all over the place. So you're going to see backward motion and stuff like that. So the way that we're doing temporal encoding is by relative positional embedding. And then relative positional embedding is something that can be generalized to longer videos. So theoretically, you could generate longer videos, but just as other models such as Animative, if you try to generate longer videos than what the model was trained on, you're probably not going to get great results, right? So you can try to generate. I mean, I guess if you don't kind of prolong the video too long, that will be okay still. But if you generate something that is twice the duration that the model was trained on, then it's not going to be great. I think it's a limitation for all models. Like if you kind of steer too far away from the distribution, you're going to get a result that is out of distribution. There is a possibility to train the model on different durations on videos, which is similar to maybe Sora, what Sora did. They kind of trained the model for different durations of videos. But then they also have that limitation of 60-second videos, because that's what the model saw during training. So you can try to generate something longer, but then nothing guarantees that you'll get significant results.
Perfect. Yeah, I think that's a great explanation.
Do we have other questions, or can we move on?
I think that's it for now. We can go back to the cinemagraphs.
Okay, sounds good. So in cinemagraphs, again, just to reiterate, when you fine-tune the model with additional signals that the model can actually use to lower the loss, the model is going to learn how to use those signals. It's going to eat them right up, because deep learning models tend to kind of use shortcuts. So when you give the model shortcuts or information that can help it lower its loss, it's definitely going to use it, okay? So that's basically the intuition that we leverage for image to video and cinemagraphs as well. And in cinemagraphs, I'll just repeat really quickly. The first frame is conditioned on the first clean frame of the video during training, just so we can get all the content in the frame exactly right and not lose information in terms of the content. And the other frames are going to be conditioned on the frame where the region that you want to animate is blacked out. And then the model is going to learn to kind of copy all the information that it sees that is not blacked out, and only generate information in the blacked out region of the video. And then during training, you can just take your image, your input image, input it clean as a clean condition for the first frame. And for the other frames, input the condition with blacked out frames in the region that you want to animate, and then get an animation only for the regions of the image that you want to animate, and the rest of the image is going to remain still. Another cool thing that we can do, again, since Lumiere is an inflated text-to-image model, we can basically do anything that you can do with the text-to-image model, with the original text-to-image model. So this is just STEdit to show you the capabilities of editing of the model. So we take an input video and noise it very significantly, and I'll touch on that in a second. And then we denoise it with a different prompt. So for example, here, made of flowers. And you can see that we turned that running woman into a running woman made of flowers. Now, touching on the very significant amount of noise that we need to add in order to induce a change. So unlike in images, when you do STEdit on an image, you don't have to use a lot of noise to kind of induce a change on the image. Videos have a lot of redundant information. So you can think about those consecutive frames that we talked about. They're pretty similar to each other, right? So even if you add a lot of noise, there's still a lot of information in those kind of consecutive frames that is repetitive. So a lot of redundant information in video generation or in video representation. So you have to add a lot of noise to kind of get rid of all that redundant information and actually induce a change to your input video. So this is just an important or kind of insight that we had for this that I kind of wanted to point out. And another thing that we can do is in painting. Again, as I said, if you fine tune the model with a signal that's going to help it get the loss down, it's going to do that perfectly. It's going to gobble it up and use that signal as much as it can. So here we fine tune the model to kind of denoise videos where some of the video information is blacked out. And then during inference, we can take partial videos and complete them or extend them or whatever it is that you want to do. For example, here we took this hot air balloon and asked it to fly around with additional hot air balloons. So you can see that the model actually created additional hot air balloons in the background. And just to show you some results of video editing, these are editing results with in-painting. So you can see that we can switch the clothes of the woman or switch the material the woman is made out of. So flowers or wooden blocks or origami or toy bricks. Yeah, so some cool video editing results that are pretty simple to achieve, actually. So all these applications that I just showed you are pretty simple to achieve with Lumiere, just because we had all this literature from text-to-image models that we could just distill to our model. Most of it was pretty simple. Some of it required some adaptation, as you saw for the stylized generation example. So I'm done. But everything I said during this talk, all the information and much more cool results can be found on our project website and also in the paper. I do hope you enjoyed it and actually got to learn something and that I was clear. I'm sorry if the talk was technical. This is the nature of kind of building foundation models. It's pretty technical, but I do hope you got something out of it and thought it was interesting.
Yeah, absolutely. I think there's some comments on the chat, but I think mostly it's like great presentation, very impressive results. I think like I personally like yeah, like super cool like that to see like the variety of downstream tasks, right, from text to video, image to video, style generation, video painting, cinemagraphs, video editing, all those things can be accomplished just by this work. So yeah,
definitely.
Yeah, I think from the last presentation you were showing a lot of interesting work on like the text to image, right? The conceptor was basically I recall you were showing like the math where you like adding subtract vector math within an image context, and now you actually can accomplish the same mechanism in the video context. So personally for me, I think it's really cool to kind of see the evolution of how different techniques, right, that allows you to process multimodal and temporal element within video and get the same output that you did when working with image modality.
Yeah, great. So thank you very much for joining, and thank you very much for your kind words. And I will say that one of the main things that I like about Lumiere is how simple the idea is and how applicable it is to almost anything you'll do with videos. And the fact that once you have that model that is fine-tuned over a text-to-image model, you can really plug and play all these applications from the text-to-image realm. And as you said, James, really do all the things that you did for images only in the video realm. And you can see kind of the correlations and the kind of co-adaptations of the temporal dimension and the spatial dimension, which is very cool.
Yep.
So I do hope this is helpful to you.
For sure. Yeah, and the recording of this presentation will be available on YouTube probably within the next 1 or 2 weeks, and I'll be sure to update the attendees as well as Hila to whenever it's become available, so we can share to a broader audience across different AI communities. And I also share all the relevant links throughout the talks in the chat, for folks who want to maybe just follow up and take a look at some of the papers that she mentioned in the presentation. And yeah, I think that's all I have. And yeah, thanks everyone for joining this session. Thanks, Hila, for giving a great presentation. And yeah, hope you have a great rest of your weekend. Cheers.
Bye. Thank you.